In this video, I'll be discussing the 2007 AMC 10B question 25. How many pairs of positive integers a, b are there such that a and b have no common factors greater than 1, and a over b plus 14b over 9a is an integer? So we have two fractions here that is an integer. The sum of the two fractions is an integer. I want to find out how many pairs of a and b satisfy this condition. Well, it's always easier to work with one fraction than two fractions in their sum, so just merge these two fractions. A over b plus 14b over 9a. Now since this equals 2, find a common denominator, 9ab, sum 9a squared plus 14b squared is integer. So this means that 9ab is a factor of 9a squared plus 14b squared. So this means that 9 is a factor of 9a squared plus 14b squared. And well, since 9a squared we already know it's gonna be a multiple of 9, so we have 9 is gonna be a factor of 14b squared, since 14b squared plus 9 squared is a multiple of 9. And now, since 9 and 14 are co-prime, so this leaves us b squared, gonna be a multiple of 9. So 9 is gonna be a factor of b squared. So 3 is a factor of b. And now we can use a common method in solving this kind of problem. If you know 3 is a factor of b, well, it might help to replace b. So like let b equals to 3n. Now we can actually do more with 3n than we can do with b because we add more numbers in the equation now. You'll see how this is helpful later on. So now, since 9a squared plus 14b squared over 9ab equals to, this is going to equal to 9a squared plus 126 n squared over, divide that, 327 an is integer. Now this will equal to a squared plus 14n squared over 3n. Just divide it. Just divide both sides, both parts, numerator and denominator, by 9. So this means that n is going to be a factor of a squared plus 14n squared, similar to the first part. And since 14n squared is already a multiple of n, to make their sum multiple of n, n has to be a factor of a squared. And now we can use the property that a and b are co-prime. Since a, b co-prime, so GCF AB, well, this equals to 1, but this also equals to GCF A and 3n. And since A, B are co-prime and B has a factor of 3, so A does not have a factor of 3. So the GCF A and 3n is going to equal to the GCF of just A and n. So we can leave 3 out. And then this will equal to, well, we're going to find pairs of positive integers. And we know this equals to 1. So to make n and a have only a GCF of 1, there's only one value of n. That's obviously 1. Because if a is any value, well, to make n co-prime is all values of a, there's only one integer known to be co-prime with all other integers, and that's 1. So n equals to 1. Because right now, a has no restriction yet. So b equals to 3n equals to 3. So 9a squared, or 9a squared plus 126n squared over 27an. Well, this will equal to 9a squared plus 14b squared. It's going to be easier to calculate, or 9ab. Now this will equal to 9a squared plus 126 over 27a. Divide both sides of the fraction sign to get a squared by 9 plus 100 plus 14 over 3a is integer. And the last part. So a is a factor of a squared plus 14. So a is a factor of 14. So a equals to 1, 2, 7, 14. And in this case, well, normally you should check if all these 4 values work, but there's a maximum of 4 values. Because b has 1 value and a has 4 values. So in total, it's going to be 4 times 1. That's 4 values in total. However, you don't even need to check if all these values work, because using the answer choices, the minimum is already 4. So we already know that the answer choices all work. All possible answers of a work. So get that a. So there are 4 pairs. Okay, now you know that the answer is going to be 4. The key point of this problem is that, first of all, we merge the fractions, because one fraction is easier to work with than 2 fractions. And then using a bit of manipulation, we get that b is a multiple of 3. So that's the first key point. And then we let b equals to 3n. And then using the GCF rule, we find that n equals to 1. Then we can finally find out the value of a. And using the answer choices, we get that a is equal to 4. Thank you for watching.